At the center of the Milky Way, hidden behind thick clouds of cosmic dust that absorb visible light, lies a silent gravitational powerhouse that has guided the motion of our galaxy for billions of years. This object, 4 million times more massive than our Sun, pulls nearby stars into a chaotic orbital dance, acting as the anchor of the entire galactic disk. For decades, astronomers have worked under the firm assumption that this object, known as Sagittarius A, is a supermassive black hole. This belief seemed to be set in stone in 2022, when the Event Horizon Telescope collaboration published the first image of the object, showing a ring of glowing plasma surrounding a central dark shadow. But the history of science shows that consensus is not the same as absolute proof. While the Event Horizon Telescope image fits the description of a black hole, it does not rule out other compact structures. The image shows a glowing disk of gas, whose light is bent by a strong gravitational field, leaving a dark void at the center. This shadow matches the predictions of general relativity for a black hole. But it can also be produced by other objects that possess similar mass and compact size. In recent years, an alternative theory has gained significant ground, challenging the fundamental nature of the galactic center. This theory suggests that Sagittarius A is not a black hole, but rather a stable, dense core of dark matter. This model proposes that the compact object at the galactic center is the dense nucleus of a vast, spherical halo of dark matter that extends through and beyond the visible borders of the Milky Way. If correct, this framework would solve two of the greatest puzzles in modern astrophysics: the nature of supermassive compact objects and the composition of dark matter. It implies that the central object and the galactic halo are not separate entities, but two parts of a single cosmic system. Challenging this consensus changes how we view gravity, space, and the evolution of galaxies. But this dark companion at our galaxy's core hides an even older secret. To trace its origins, we must look back to a series of bizarre radio signals detected nearly a century ago, and a star that orbits the dark abyss at a speed that shouldn't be possible. The journey to understanding Sagittarius A began in the 1930s when Carl Jansky, a pioneer at Bell Laboratories, detected a persistent radio hiss coming from the heart of our galaxy. Jansky was investigating sources of static that might interfere with overseas communications. He noticed a daily cycle in the signal strength that aligned not with the Sun, but with the stars. At the time, the concept of a black hole was still considered a mathematical anomaly. Astronomers debated whether this strange signal came from gas clouds, dense star clusters, or supernova ruins. In 1974, Bruce Ballack and Robert Brown pinpointed the source as a single compact object, naming it Sagittarius A. In the 1990s, advances in infrared astronomy and adaptive optics allowed observers to look through the dust clouds. What they found was shocking: a group of stars orbiting this empty region at extreme speeds. These stars, known as S-stars, are the closest observable objects to the galactic center. The star S2, for example, travels at velocities reaching 24,000 kilometers per second, which is 8% the speed of light. It completes a full orbit in just under 16 years. By tracking these orbits, astronomers calculated that SCAR A has a mass of 4.3 million suns, confined within a region smaller than the orbit of Venus. This research, led by Reinhard Genzel and André Ghez, earned them the Nobel Prize in Physics in 2020. Crucially, the Nobel citation referred to the discovery of a supermassive compact object at the galactic center, rather than calling it a black hole. This choice of words highlights the ongoing quest to confirm the physical identity of this object. The orbits of these S-stars act as a natural laboratory, allowing physicists to test gravity in the strongest fields available in our galaxy. But as astronomers tracked this star's impossible speed, they realized the orbit was hiding a fatal flaw, a discrepancy that threatened the very definition of a black hole and pointed to a mystery dating back to the dawn of time. But before we look at the cosmic anomalies that challenge Einstein himself, if you want to explore the deepest mysteries of the signal, make sure to subscribe to Deep Space Signal. Doing so connects you with a community of explorers searching for the truth about our place in the cosmos. Void. Now, what did these orbital anomalies actually reveal? One of the most persistent problems in modern cosmology is the origin of supermassive black holes. While stellar mass black holes form when a massive star collapses under its own gravity, there are no stars large enough to collapse directly into an object with millions of solar masses. To grow a black hole to the size of Sagittarius A through the slow accumulation of gas and stellar collisions requires an enormous amount of time. Yet, when we look at the early universe, we find supermassive black holes already fully formed, existing less than 1 billion years after the Big Bang. This rapid growth is constrained by a fundamental physical limit, known as the Eddington limit. When gas falls toward a black hole, it heats up due to friction and gravitational compression, emitting intense radiation. The outward pressure of this light pushes against the incoming gas. If a black hole tries to swallow matter too quickly, the radiation pressure literally blows the fuel supply away. This sets a maximum speed limit on black hole growth. To explain how supermassive black holes existed in the early universe, they must have started as incredibly massive seeds, but standard physics fails to explain where these giant seeds came from. For a star-sized seed to reach millions of solar masses in such a short cosmic window, it would have to swallow matter at rates that violate the laws of physics. This paradox has forced astrophysicists to look beyond the standard model of black hole evolution. If the universe could not build these objects through normal means, then perhaps they are not black holes at all. This brings us back to our galactic center, where researchers are testing a model that bypasses the need for seeds entirely. But to understand how scientists coordinate this global effort, we must first look at how researchers cross boundaries to share their work. Major discoveries in astrophysics are rarely the work of a single individual. They require international collaboration, bringing together research teams from across the globe who must communicate and share data despite speaking different native languages. That is where today's sponsor, Babbel, comes in. Babbel is one of the leading language learning applications in the world, designed to help you start speaking a new language in a short time. Unlike traditional methods that focus on memorizing list vocabulary, Babbel teaches practical, real-world conversations. The lessons are curated by language experts and backed by academic research, helping you build the confidence to navigate new cultures. Whether you are traveling for an astronomical event, like the upcoming solar eclipse in Spain, or boosting your career in an international field, Babbel provides a structured, accessible path to language learning. Babbel is offering our viewers a 55% discount on their subscription. You can access this offer by scanning the QR code on the screen or by clicking the link in the description below. Babbel also offers a 14-day money-back guarantee, allowing you to try the application with complete confidence. Now, let us return to the Galactic Center to examine how researchers are testing the dark matter core hypothesis. In February 2026, a study published by Valentina Crespi and her colleagues at the Institute of Astrophysics of La Plata in Buenos Aires brought this alternative model into the spotlight. The team analyzed this cosmic dilemma by comparing a model where Sagittarius A is a dense dark matter core against the precise orbital data of the star S2 and 5 unique G objects. G objects are strange structures that look like gas clouds but behave like stars. They stretch dramatically as they approach star A, yet somehow manage to stay intact. The results of the study were startling. The dark matter core model reproduced the S2 and G object orbits with a difference of less than 1% compared to the classic black hole model. This statistical match demonstrates that based on current orbital observations, a dark matter core is dynamically equivalent to a supermassive black hole. Both models exert the exact same gravitational influence on their surroundings at these distances. This equivalence raises a much broader question about the nature of dark matter itself, first proposed by Fritz Zwicky in the 1930s to explain the unexpected speeds of galaxies in clusters, and later confirmed by Vera Rubin's study of galactic rotation. Dark matter has remained an invisible ghost in our equations. But now, it seems this ghost might be concentrated at the very center of our galaxy. The G objects provide a highly sensitive test for these competing theories. Because they are extended structures rather than single points of light like stars, their gaseous envelopes react strongly to tidal forces. The way these envelopes stretch and deform as they fly past the central mass tells us a lot about the local gravitational field. The fact that the dark matter core model can match these deforming envelopes with the same precision as a black hole shows that the gravitational potential is identical at these distances. However, this raises a massive contradiction. If there is no singularity at the center, what is stopping this massive pile of dark matter from collapsing under its own weight? The specific dark matter model tested by the La Plata team is based on the Ruffini-Argüelles-Rueda model, first proposed in the late 20th century and refined in recent years. This framework suggests that dark matter consists of dark fermions. Fermions are a class of subatomic particles, including electrons, protons, and quarks, that obey a strict quantum rule known as the Pauli exclusion principle. This rule states that no two identical fermions can occupy the exact same quantum state at the same time. This principle is what prevents regular matter from collapsing under its own weight, allowing atoms and thus our physical world to exist. Because of this quantum rule, dark fermions resist being squeezed together indefinitely. When gravity pulls them inward toward the galactic center, they generate a powerful quantum degeneracy pressure that opposes further collapse. If the mass of the particles is in the right range, this pressure can support a stable, ultra-dense core, preventing the particles from collapsing into a singularity or forming an event horizon. The result is a compact object with the mass of a supermassive black hole, but without the infinite density of a singularity. This represents a stable alternative that avoids the mathematical problems of infinite collapse that plague the classical theory of black holes. The key feature of this model is its ability to link the central object with the rest of the galaxy. Instead of treating Sagittarius A and the surrounding dark matter halo as separate structures, the fermionic model shows they are part of a single continuous distribution. The core is the ultra-dense quantum region at the center, while the diffuse halo extends outward across the galaxy. This unified structure naturally explains the behavior of stars at both the center and the outer edges of the Milky Way. But as researchers looked closer at the edges of our galaxy, they detected a sudden change in stellar speeds, a drop-off that standard dark matter models could not explain. This sudden speed drop is known as the Keplerian decline. In 2022, data from the Gaia Space Observatory showed that the orbital speeds of stars at the outer edges of the Milky Way decrease much faster than previously thought. This was a massive surprise. Standard models of dark matter halos describe them as diffuse clouds that thin out very slowly, which should cause stellar speeds to remain constant or drop off very gradually. A fermionic dark matter halo, however, behaves differently. Because it is governed by quantum mechanics, it has a distinct physical boundary defined by the limits of quantum degeneracy. This sharp drop in density at the edge of the halo explains the sudden drop in stellar speeds observed by Gaia. For the first time, a single theory could explain both the extreme gravity at the center of the galaxy and the behavior of stars at the very edge. This unified framework represents a major shift in how we model galaxies. Instead of treating dark matter as an arbitrary shape added to equations to fix gravity, the fermionic model treats the galaxy as a single, coherent quantum system. But this leads to an even bigger question. If Sagittarius A is indeed a giant core of dark matter with no event horizon, why haven't we seen matter colliding with it? Normally, if gas falls onto a compact object with a solid surface, like a neutron star, it crashes into it at relativistic speeds, releasing a torrent of thermal radiation and X-ray flares. Yet Sagittarius A is famously quiet and dim. Do you believe Sagittarius A is a classic black hole, or are we looking at a giant ball of quantum dark matter? Let me know your theory down in the comments, because what we're about to reveal next about how gas interacts with this dark core changes everything. The lack of massive thermal flares is the strongest argument used by supporters of the black hole model. In standard astrophysics, if an object has no event horizon, it must have a physical surface. When gas falls toward it, the gas should collide with this surface, converting its kinetic energy into heat and light. This process, called surface accretion, makes objects like neutron stars shine brightly. Because Sagittarius A does not show this intense surface radiation, most physicists assume it must have an event horizon that swallows the gas and its energy forever. But the dark matter core model provides an elegant solution to this problem. Dark matter, by definition, does not interact with electromagnetic radiation or regular matter through electromagnetic forces. It only interacts through gravity. This means that a core of dark fermions does not behave like a solid wall of rock or metal. It is, for all practical purposes, a ghost surface. When gas falls toward the galactic center, it does not crash into a solid barrier. Instead, the gas particles simply glide through the diffuse outer layers and even the dense inner core of the dark matter distribution. As the gas passes through the core, it experiences only the gravitational pull of the dark fermions. The gas is accelerated, heated, and bent by gravity, emitting the radio waves we observe, but it never hits a hard surface. It simply swings through the center and continues on its orbit, or settles into a complex disk. Because there is no physical collision, there is no surface thermal signature. The dark matter core behaves exactly like a black hole in terms of radiative efficiency, hiding its lack of an event horizon in plain sight. But this ghostly behavior is not limited to our own galaxy. If we look further back in time, to the very beginning of the cosmos, this model resolves a mystery that has left space telescopes baffled. The ghost surface hypothesis does more than explain Sagittarius A. It also offers a solution to one of the most shocking discoveries made by the James Webb Space Telescope. Soon after it began sending data back to Earth, the telescope detected a population of objects that astronomers nicknamed little red dots. These objects are extremely compact, highly massive structures that existed less than 1 billion years after the Big Bang. In the standard model of cosmic evolution, there simply was not enough time for normal stars to collapse, form black holes, and grow into these supermassive beasts. In the dense, cold conditions of the early universe, dark fermions could have collapsed directly into compact configurations. Unlike regular gas, which must cool down slowly by emitting light before it can collapse under gravity, dark matter does not interact with light. It can fall directly into gravitational wells. Once the density of these collapsing dark fermions reached the quantum degeneracy threshold, a stable core was established immediately. This direct collapse mechanism bypasses the need for a stellar precursor, explaining how these massive structures could exist so early in cosmic history. This model suggests that the structures at the centers of these early galaxies were not grown slowly, over hundreds of millions of years. Instead, they were established as primordial dark matter cores during the initial stages of cosmic structure formation. These dark cores then acted as gravitational anchors, pulling in normal hydrogen and helium gas to form the first generations of stars and the host galaxies themselves. This completely flips our understanding of galactic evolution. Galaxies did not grow black holes at their centers. Rather, dark matter cores grew galaxies around them. But to prove this theory, we must find a way to look directly at the boundary of Sagittarius A and see if it truly lacks an event horizon. To determine which model is correct, astronomers are searching for unique physical signatures that only a true black hole can produce. A genuine black hole possesses an event horizon, which creates a very specific optical feature called photon rings. These are sharp, nested rings of light formed by photons that orbit the black hole multiple times before escaping to our telescopes or falling into the singularity. Because a dark matter core lacks a singularity and event horizon, it cannot produce these infinite, nested photon rings. Instead, light passing close to the core is bent but not captured in permanent orbits. Imaging these thin rings of light requires a level of resolution that is far beyond our current ground-based arrays. The Event Horizon Telescope has pushed ground-based radio interferometry to its absolute physical limit. To achieve the resolution needed to see the fine details of the photon rings around Sagittarius A, we must expand our network of telescopes into space. This is the goal behind NASA's proposed Black Hole Explorer mission, which plans to place a high-frequency radio telescope in orbit around the Earth. By linking a space-based telescope with ground arrays, astronomers can create a virtual telescope larger than the diameter of our planet. This configuration would eliminate the atmospheric distortion that blurs high-frequency radio waves, allowing for much cleaner signals and higher contrast imaging. If the nested photon rings are detected, it will confirm the existence of an event horizon, proving that Sagittarius A is indeed a black hole. If they are absent, it will suggest that the object lacks a singularity, providing the first direct evidence for a compact dark matter core. But while space telescopes prepare to map the heavens, another group of physicists is looking deep underground. While space missions are still on the drawing board, ground-based observatories continue to collect critical data. The gravity interferometer at the Very Large Telescope in Chile is currently tracking the orbital precession of the star S2. Each orbit S2 completes around Sagittarius A shifts slightly in orientation due to the effects of general relativity. The exact rate and direction of this shift depend on how mass is distributed at the center. A single point mass black hole and a distributed dark matter core produce different precession signatures, allowing astronomers to test these models as more orbits are completed. At the other end of the scale, particle physicists are looking for the particles that make up this dark core. The NEON experiment in South Korea, for instance, uses high-purity detectors placed deep underground in the Yemi laboratory to search for the minute interactions of dark matter. If dark fermions exist, they should occasionally scatter off atomic nuclei, leaving a small thermal or electrical signature that can be detected in deep underground chambers, shielded from cosmic rays. The elegance of the fermionic dark matter model lies in its ability to connect the smallest, subatomic scales with the largest structures in the universe. It suggests that the mysterious dark matter that holds galaxies together is also responsible for the compact beasts at their centers. If you want to support our work and access ad-free content, consider joining our Patreon page using the link in the description. Your support allows us to continue creating educational content, exploring the physics of the cosmos. As our instruments improve, we move closer to resolving the nature of the dark companion at our galaxy's center. Whether it turns out to be a classic black hole or a dense core of quantum matter, the search itself drives our understanding forward. The center of our galaxy remains a window into the fundamental laws of physics. If you were shocked by what the Event Horizon Telescope found here, you need to see what it detected in this other galaxy in this video here.